In this video, we're going to be looking at some examples where we use the tools of manipulating series, like substituting something for x and multiplying by some term, as well as differentiating a power series to create new power series. So we're going to be using the following fact in these different examples, that we know that 1 over 1 minus x equals the power series that is the sum from n equals 0 to infinity of x to the n for the absolute value of x less than 1. Okay, so in our first example, we're interested in finding the power series representation for f of x equals 1 over 1 plus x squared. And in both example 1 and example 2, we're going to be using manipulation of series. So we're going to try to see how our given function here is similar to the fact that we know, and how we can manipulate our given function to make it look something like this fact that we already know. So notice that 1 over 1 plus x squared can be rewritten as 1 over 1 minus negative x squared. Okay, so that I can look at my function here as being a composition of this given function, 1 over 1 minus x, and negative x squared. So since 1 over 1 minus x equals the sum of x to the n, 1 over 1 minus negative x squared will be equal to the sum from n equals 0 to infinity of, well, here x was what I was raising to the n, so my new, my new x, okay, what I'm substituting for x here, plugging in for x, will be negative x squared. Okay, notice that this statement here was true when the absolute value of x is less than 1. The thing that we've substituted is negative x squared, so this is going to be true when negative x squared in absolute value is less than 1. And then we can go about simplifying this a little bit. So using exponent rules here, I have negative 1 times x squared being raised to the n. So that's negative 1 to the n, and then x squared to the n. This negative x squared in absolute value would be just x squared less than 1. And we know that the absolute value of x squared will be less than 1 when absolute value of x is less than 1. Or you can think about absolute value of x squared equals the absolute value of x squared. Okay, and then we're just taking the square root of both sides. So to finish this off here, I could write this as my sum from n equals 0 to infinity, negative 1 to the n, times x to the 2n, where absolute x is less than 1. Okay, so now we have a power series representation for 1 plus x squared, just by doing this substitution technique. Okay, so let's look at another one where we do some kind of manipulation. Let me rewrite the fact that we have. We know that 1 over 1 minus x is equal to the sum from n equals 0 to infinity of x to the n, where absolute x is less than 1. Okay, that inequality holds where absolute value of x is less than 1. So the series, or excuse me, the function that I'm given is x over 8 minus x cubed. Okay, so this is going to have multiple steps to manipulate this to make it look like 1 over 1 minus something, or maybe some constant or some additional term times 1 over 1 minus something. So notice I can write this as x times 1 over 8 minus x cubed. Okay, and then I'd like that 8 to actually be a 1. So I'm going to do some factoring here and say this is x times 1 over 8 times 1 minus x cubed over 8. Okay, so I can pull out x over 8 then in front, say I have x over 8 times 1 over 1 minus x cubed over 8. Okay, and now I see this is in the form 1 over 1 minus something, and I have this x to the 8th out in front. So I can say that this is equal to x to the 8th times the series here that would represent 1 over 1 minus x to the 3rd over 8. So I'm going to be replacing x to the 3rd over 8 in here for x, doing a substitution. So we have, this is now the sum, n equals 0 to infinity. Instead of having x to the n, I'm going to have x cubed over 8 to the n. okay? And this is true when x cubed over 8 in absolute value is less than 1. Okay, so we just want to simplify this a little bit. So I can come over here and say this is x over 8 times the sum from n equals 0 to infinity. This x cubed over 8 to the n means I'm going to have x to the 3n over 8 to the n. And then I can take this x over 8 and bring it inside the sum, okay, because this is like x over 8 times a sum of several terms, so I can think about distributing the x to the 8th over each of them. So what I'm looking at is a sum of x to the 8ths times x to the 3n's over 8 to the n. So I'm writing out a few more steps than you would necessarily have to show all the time, just to show you the in-between work. So this is n equals 0 to infinity. I'm going to have x to the 3n plus 1 over 8 to the n plus 1. Okay? And let's see, we said that this was going to be where x cubed over 8 was less than 1. That means that x cubed is less than 8, okay? Or x is less than 2 in absolute value, okay? So just to summarize here, we can say that our function x over 8 minus x cubed turns out to be equal to the sum from n equals 0 to infinity of x to the 3n plus 1 over 8 to the n plus 1, where our absolute value of x is less than 2. Okay, so this shows you a couple of the kinds of manipulations that we'll do with substituting things for x, sometimes factoring something out, and also multiplying maybe our series by some additional term on the outside there. Okay, so we'll see several examples throughout this section where we do some kind of manipulations like this. We also have another tool which is using differentiation to find new power series. So again, remember that 1 over 1 minus x is equal to the sum from n equals 0 to infinity of x to the n, where absolute value of x is less than 1. Everything that we're doing in this section is involves starting from this point, because this is the only function that we knew to begin with, but then I can create new functions for this, and then I can use additional tools on those new functions' power series. Okay, so far, I've created power series for 2 additional functions. So what do I want to notice here? I'm saying I'm going to use differentiation. What's the relationship between 1 over 1 minus x and 1 over 1 minus x squared? Okay, well, notice that the derivative of 1 over 1 minus x, okay, is negative 1 minus x to the negative 2 times negative 1. So that is exactly 1 over 1 minus x squared. Okay, so if I take the derivative then of both sides of this equation, so the derivative of 1 over 1 minus x, the derivative of the sum from n equals 0 to infinity of x to the n, the left-hand side here, that's the function I'm trying to represent, 1 over 1 minus x squared. And then I have my theorem that says to take the derivative of this infinite sum, I can just do the sum of the derivatives of each of my terms. So this is my term-by-term differentiation, it's called. So I have n equals 0 to infinity. Derivative of x to the n is nx to the n minus 1. Okay, and our radius of convergence is staying the same. This is still going to be r equals 1. I'll also still actually have the interval of convergence being from -1 to 1, or with absolute value of x less than 1. There's one additional step I can do here to simplify things if I want. Notice that when n equals 0, this term is just going to be 0. Okay, so this is the same thing as saying the sum from n equals 1 to infinity of nx to the n minus 1. So you might often see it expressed like that. Okay, and I just want to note that you could keep doing this. You could do this a second time if you wanted to find the second derivative. So we could do the derivative of 1 over 1 minus x squared equals the derivative of the sum from n equals 1 to infinity of nx to the n minus 1. Okay, so our derivative of this is going to be -2 1 minus x to the -3 times -1, or 2 over 1 minus x cubed. Okay, and that will be equal to than the derivative over here, which is the sum from n equals 1 to infinity of n times n minus 1 times x to the n minus 2. And again, we could simplify this if we chose a little bit. Since n equals 1, the first term here will be 0, so if I just want this to start with the first non-zero term, I could write it as a sum from n equals 2 to infinity of n times n minus 1 x to the n minus 2. Okay, so I've created more series representations of additional functions. Okay, so this reviews the tools of manipulating series and differentiating series. Watch the next section of videos to see how we use the integration tool to create new power series.